As you can see on Riana's first slide, first of all, she's from Stellenbosch, the University of Stellenbosch, and her talk is on how to locate a robber on a graph. But before we ask her to continue with her lecture, a bit more about Riana. She's a lecturer at the Stellenbosch University, and she works in the field of graph theory. Her main focus falls on the protection of graphs with specific interest in domination and variations thereof. She also enjoys games on graphs and how parameters of a graph behaves when the graph itself changes. Riana, thank you for giving this lecture, and now over to you.
Thank you, Betsy. So, good morning, everyone. I thought that I will start by telling you what the aim of this presentation is, because I sometimes get really upset with my husband if he doesn't start with explaining the aim of something before we do it. So the aim of my talk is not to give you a very mathematical talk, but to give you an idea about what the localization game on a graph is about and how it's played, and just like the natural progression from the idea to where I am now in a project that I'm working on. So the title suggests exactly how this game is played. We want to find a robber on the graph. It is, it's really a game of cops and robbers. So what I'm going to do is I'm going to start by finding the right button, by giving you an idea of what the localization game is, how it's played. We're going to do an example to make sure that you understand how it works. Then I'll look at some general results, just some of them. There are many more that we can consider, but I just want to focus on the basics. We're going to then move on to some special graph classes and to see how this parameter works on these graph classes. And then I'll conclude the presentation with some open questions. Now, I can remember I once spoke to a colleague from, I think, Slovakia, and he said his wife always jokes around that he's a professor and the only thing he does is he colors graphs for a living. So I think it's pretty neat that I can play on a graph for my research. So the game of the localization game of the robber comes from the very well-known game of cops and robbers on graphs. Now this game, I think, was introduced in the 1960s. And how it is played is as followed. The cops is somewhere on the graph. You can imagine a real-life cops and robbers situation if you want to. Then they get information to tell them that the robber is at some point in this graph. So they know exactly where the robber is in this stage. They just want to find him. So it's a pursuit evasion game. The cops then get an opportunity to run after this robber, to corner him in some way, so they can move to any place in their neighborhood. If after that step, the cop is on the same vertex as a robber, then he can catch him, obviously. They're in close contact with one another and the cop wins. If that's not the case, the robber has opportunity to run further. If he has a great hiding place, he can stay put. Otherwise, he can move to somewhere in his neighborhood. And then this game continues on a turn-based, or it's a turn-based game. So then the cops get a chance to run after the robber again. The robber gets to run away if the cops doesn't catch him. And this game continues like this until either the cop wins, or if the robber manages to evade the cop forever, then the robber wins. And what we're interested in this game is in a cop number, which would be the minimum number of cops that's needed to win. Now, if I think about this game of cops and robbers, I imagine it being what chasing a robber looked like in the 70s. So I imagine a cops and robbers show, TV show, when I see this problem. And the localization problem that we're talking about today is more like the 21st century kinds of cops and robber game. The cop is sitting there in his office. He's not going to get his hands dirty running around after a cop. He's rather going to use technology to give him information. And then if he knows where this robber is, he'll just send in the chopper. I think that is the main difference between the two. So if we think about this in terms of how it works, there's a few things that's really different to the game, but the whole idea of finding the robber is kind of the same. So when we think about the cops and robber game, the cops always knew where the robber were or was, and they just chased him around. In the localization game, the cop has no idea where the robber is when they start. That is the aim of the game, is to locate the robber, not to catch him, to locate him. Catching is someone else's problem. So when we start, it's an unknown position for the robber. Then after that, the cop sits there in his office and he probes K vertices on the graph. You can see this in as the cop asks K informants if they saw the robber, or he pings a cell phone tower to get some distance from the guy's bracelet that was a prison bracelet or something like that. So they receive then from these probes the distance that the robber is from each of these vertices. It will be the blue ones. If after this information, he received this information, if the cop can then determine where the robber is located, the cop wins. Otherwise, the robber can change his hiding place or run away. And you can see here that the robber can only move to its neighboring vertices because the robber is located on the graph. He runs around on the graph. He can never jump over vertices. He can just go to his adjacent vertices. But the cop, because the cop is not on the graph, he's somewhere else, he can probe any K vertices after that. It can be the same ones, it can be different ones, it can be far away from the initial probe, anywhere. After that, he receives distance again, and this game continues until either the cop wins in a finite number of times or the robber evades the cop forever. In this case, same as before, we are interested in the minimum number of vertices that the cop chooses, so the minimum number of probes, and that is called the localization number of the graph. And this is the parameter that we are going to look at today. So before we look at the properties of this parameter, let's just look at an example and see how this game is played on a proper graph. We are going to look at the complete bipartite graph K34, and I'm going to show that the localization number is equal to 3 by first showing that it's not equal to 2. So 2 cops or 2 probes aren't enough, but 3 are definitely enough. So this is the graph K34. There's 3 vertices in the one partite set here at the bottom and 4 at the top. And first, let's just convince ourselves that it is not going to help to probe 2 vertices. My probed vertices are the gray vertices. If we probe 2 vertices in the same partite set, then the other partite set will have exactly the same distance to those 2 probed vertices. And then the robber can just be anywhere in the graph again in the next turn. So it is necessary to probe 1 vertex at the top and 1 vertex at the bottom to see whether the strategy will work. So in this first graph, the green and the red vertices shows the 2 sets where the distances to the gray vertices are the same. Let's, for example, look at the green set over here. Each vertex in this green set is distance 1 away from the top vertex and distance 2 away from the bottom gray vertex. So they have the same distances to these 2 vertices. The same is true for the red vertices at the top. It is distance 1 from the bottom gray vertex and distance 2 from the top gray vertex. So what happens essentially is that the robber can hide either in the red vertices or in the green vertices. And to show that 2 probes is not sufficient, what we want to show is that no matter what the cop do, the robber will always be able to find a strategy where he can win. So there will always be something that the robber can do to get away from the cop. So it doesn't mean that in no circumstance the cop can accidentally probe the right vertex. We just want to show that there exists a strategy for the robber to evade the cop. So let's look at the 2 cases. the robber can either be located on the green vertices. That means after the probe, the CoP receives the distances 1, 2 from the probes. So if it's green, then after that probe, the robber can be anywhere here in the blue shaded area. So after the robber has moved, and he can be anywhere in the blue area, we probe again. We probe one at the top, one at the bottom. And then we can see that the robber can't hide anymore in the bottom partite set, but he can hide the top one. And those top 3 red vertices, it's exactly the same set that we had in the beginning. So we know that we will get the same situation. If we have that situation of the 3 red vertices, we continue. The robber can now move anywhere in this blue, light blue area. And we have 2 cases, either green or red. The green one looks the same as the first one, so we'll just be in that case again. If it's red and we probe again, then we again find a green set that looks like the first one again. So it shows that it doesn't matter what we probe. The robber will always have a strategy to get away. So he will be able to infinitely evade the CoP's pursuit. Okay. So 2 is not enough. Now to show that 3 is enough, we're going to probe 2 vertices in one partite set and 1 in the other partite set to ensure that we can find this. So you can see that if the vertex is in the bottom partite, another vertex, if the robber is in the bottom partite set, then we can immediately catch him because there's no other vertices that's colored green. But he can still hide in this top part and the red vertices. So after that, you can go anywhere in this blue area. We probe 3 again, and you can see that we have now decreased the set that he can be in. So then in the next step, the robber can be in a smaller part of the graph, and then we have enough probes in order to find the robber. So just after 3 steps, we know that the robber is, or where the robber is located, and someone else can go and pick him up. So the localization number of the complete graph K34 is equal to 3. So now to go from here, from the game, and we know how it's played, we want to start thinking about bounds on this parameter. So what kind of values can this parameter have? So nice upper bound to it, lower bound, and so forth. So to find a very natural upper bound, we have to look at another parameter of a graph, which is called the metric dimension of a graph. And the metric dimension of a graph is the minimum cardinality of a resolving set. And a resolving set is a set of vertices where all the other vertices in the graph can be uniquely determined by the distances to the vertices in S. So if we listen to that again, all the other vertices can be uniquely determined by the distances to S, which means if we think in terms of the localization again, if we probe all the vertices in a resolving set, then we can immediately catch the robber. So in that case, it is an upper bound to the localization game. Might be less because we can do it step after step. So just to illustrate the metric dimension of a graph, we've seen like 2 slides ago, go back, that if we look at this complete bipartite graph, that 3 vertices won't form a resolving set because there is a set where the robber can hide. If we now pick 4 vertices, there's 2 options for 4 vertices, we can see the same thing happen. In this first case, we have 2 green vertices, and in the second one, we have 2 red vertices. And we don't want vertices with the same distance. We want them to be uniquely determined by the distances. So we need at least 5 in this case in order to uniquely identify the remaining vertices by their distances. And so then we get this very nice upper bound. So the upper bound of the metric dimension and lower bound of 1, because if we have no CoPs, nothing's ever going to happen. Okay. So the question we should ask ourselves is this a good bound? Can the localization number be equal to the metric dimension, or will it always be smaller? And can we find graphs where the localization number is equal to 1? Now, for the lower bound, there's actually a huge class of graphs for which this is true. This is, in fact, where the localization game started. The question in the beginning was just whether one CoP can locate a robber on a graph, and then it evolved from there. So there are many of them, and we'll look at some of those classes in a little bit. For the metric dimension, we surely have graphs for which it is reached as well, because, oh, sorry, this is me writing one before. Most likely just leave it there too. So if we can show that the complete graph has the localization number and metric dimension equal to one another. And the reason for this is if we pick less than n-1, so all but one of them, if we pick less than that, then the remaining vertices, these three, will have exactly the same distance away from these black vertices, which means it is a safe set for the robber. And then in the next step, the robber can be anywhere on that graph again. So therefore, we need at least n-1 vertices in order to catch the robber. In fact, when we talk about complete graphs, it is true that for a robber to be found on that complete graph, we have to find a set that resolves the vertices in that complete graph. So the robber, your probe can never leave a safe set in the complete graph, because otherwise, afterwards, the robber can just be anywhere in that complete graph again. Next example that I want to look at that has got to do with this inequality is a case where we have a graph where the difference between the localization number and the metric dimension can be arbitrarily large. And we do that with an example of a star. Now, in a star, we can find the metric dimension as s-1. That would be one less than the number of leaves. And in the same way as with the complete graph, I'm sure you can convince yourself quite easily that if I pick less than s-1 vertices, then the remaining leaves will be in the same safe set. So a robber would be able to hide there. So if I pick just 3 of them, it means that I'll have 2 vertices, which has the same distance away from those vertices. And that tells us that the metric dimension of a star is 1 less than the number of leaves. However, if we look at the metric, excuse me, swapping them around, the localization number of a graph, 1 CoP is enough to find a robber hiding on a star. And this little diagram, it might look very familiar because it follows the same strategy as that of the complete bipartite graph K3-4. And the reason for that is because this is also a complete bipartite graph. So what we do is we probe one of the leaves, that's a gray vertex in the first block. Then the center vertex is uniquely determined, but all the other leaves are 2 away from that probed vertex, and the robber can be somewhere there. Then in the next step, the robber can't go back to the probed vertex. So we are decreasing the area where the robber can be. And we continue in this way, probing leaf by leaf until we can catch the robber, which would be on one of the leaves. So we can easily show that the localization number is 1. And now you can see that this difference between the two can be as large as possible. So what have we seen? Well, we know that the localization number can be 1. We know that the localization number can be the metric dimension, which might be n-1. What happens in between? Can we find a graph of order n and which has a localization number for every value between 1 and n-1? So if you give me a value k, can I find a graph of order n with localization number k? And the answer is yes, we can. We're going to make use of this idea of the structure of a star and just expand on it a little bit. So in this example, this is a graph of order n. We can show that it has localization number k. And the graph is constructed as follows. We take a star and we expand the center of that star, or explode the center of that star to become a complete graph of the order that we want the localization number to be. And we make sure that the leaves of the star is connected to all the vertices in that complete graph. when I prepared this, I thought maybe we should call this the supernova graph. It's an exploded star. That's nice. And it's not too difficult to show that this graph has localization number k. It follows the same kind of argument that with the star. We just have to ensure that the CoP can't hide in this complete graph in the middle. It's indicated with black, and we need at least 4 vertices for that. So if we have that, then one by one, we can cut off these stars leaves, or the original stars leaves, in the same kind of argument that we have with the star. So we can always find this, everything's possible. What makes the structure nice as well is that you can show that there exists a sequence of graphs where the localization number goes from 1 to k, and the smaller one is a subgraph of the next one. So you can build up these graphs gradually and find one for each value between 1 and n-1. Now, in these past few slides, we spoke a lot about a complete graph, and that we always need n-1 to make sure that we can catch a robber, n-1 probes, to make sure we can catch a robber on a complete graph. And this might lead you to think that we can maybe increase the localization number's lower bound to have something to do with the clique number of a graph. So for those of you that is familiar with colorings in graphs, this is the same idea that's used there. So you have to have a certain number of colors in terms of your largest complete subgraph. Unfortunately, it's not the case for the localization number. Let's look at this example here. I call this first one the double house graph, a house with a weird roof to the side. So you can see that in this graph, we have a complete graph of order 4, so all possible edges between these 4 vertices. And if we had that graph on its own, then we would need 3 probes in order to find the robber. But if we probe the 2 top vertices of the 2 roofs, the 2 black ones, then we can immediately locate the robber. And you can see that by the distances indicated on this graph. So just the subgraph of a complete graph is not enough to show that we need n-1 or clique number -1 vertices. The other thing that I want to illustrate with this example is that the parameter does not necessarily decrease if we take a subgraph of the original graph. So what we're saying is that the parameter is not monotone and taking subgraphs. So if we make the graph smaller, it doesn't always mean that the parameter is going to get smaller, because if we take V away and we're left with the house graph on our right-hand side, then 2 vertices can't find the robber. And the reason for that is that the robber will always have a place to hide in the clique, and then he can just be anywhere in that graph again. Okay. We can say something about a clique. We can determine what is the largest clique that we can have for a certain number of vertices, and then get a bound in terms of the clique number for the localization number. I want to mention here that there are many of these results regarding the localization claim that is very similar to results in the metric dimension, because the extremal cases for these 2 parameters many times they overlap. So in this case, let's see why we get this lower bound in terms of the clique number. Now, the clique number of a graph is the cardinality of the largest maximal complete subgraph in a graph. So the largest set of vertices that's all connected in our graph. And we are going to show that if we have k-probe vertices, then the largest value that this clique can have is 2 to the power of k. So imagine that our localization number is equal to k, and we are looking for the largest clique. So the largest clique can only happen if we probe from outside of that clique. So our probe vertices will be these ones here at the top. And we want to see how they are connected to the vertices in this clique, K omega. And what we're going to do is we're going to give each of these vertices a tuple that indicates how they are connected to the probe vertices. It's going to receive a 0 if the distance between the probe and the vertices in the clique, the minimum distance, is the same as the distance to that vertex, and 1 if it's not the same. I just want to change the wording a little bit to make clear what happens here. Let's say that this probe vertex is adjacent to a vertex in the clique. If that happens, we're going to give it a value of 0. If it's not adjacent, then we know it would be of distance 2 away from that probe, because if we can find one where it is adjacent, then there is an edge between the vertex and any other vertex in the clique. So a 0 if it's not, when it is adjacent, and a 1 if it's not adjacent. So these tuples tells us how the vertices are adjacent, whether they are adjacent to the probe vertices. And in order for us to locate the robber in this clique immediately, we have to find a way for all of these tuples to be different, because if all of them are different, then we immediately know where the robber is. And if we have a k tuple, then we know that there are 2 to the power of k ways in which we can choose the tuple, I mean. And therefore, the largest cardinality of a clique will be 2 to the power of k, which gives us our lower bound. So this just shows us that a robber can't hide in a clique from the localization number of the clique's robbers. So we need some other ideas about when can a robber hide to determine what the localization number would be. So we can show that a robber can hide from a cop if there's small cycles, which means that the robber can run in circles and then he can continually evade the cop. So this theorem says that if we have a cycle of less than 6, then a single cop will never win. We need at least 2 cops. I want to show why this is so by just quickly looking at the example of 4 cycle. So if there's a 4 cycle in a graph, then there's only one of 2 things that can happen. Firstly, we need to convince ourselves that one single probe cannot uniquely identify all the distances in a 4 cycle. So there will always be at least one safe set for the robber. And that safe set would either contain a diagonal safe pair, like in the first graph, or an adjacent safe pair like in the second graph. And if that happens, so if the robber is safe at these black vertices, then in the next step, the robber can be anywhere in that cycle again, which just brings us back to square one. So if there's a small cycle, the robber should just stay in that small cycle and run away from the cop continuously. This brings us to special graph classes. So at this point, I just want to note that there are some other bounds on the localization number in terms of maximum degree, in terms of path width. Well, maybe I just can't think of everything now, but there are more. But I just want to give you an overview of this. So we're not going to go into the details of all possible bounds. I would rather want to look at a very easy type of graph that you would like to consider when you find new parameter, because it doesn't contain cycles, and that is the graph class of trees. So whenever we have a acyclic graph, it's sometimes easier to play this because specifically of the thing that the robber can't run in a circle. So the cop can maybe chasing into a branch of the tree. So our question is, can a robber hide from a cop in a tree, from a single cop? And the answer is sometimes. I have 2 trees here. And my question is, in which one of these can a robber hide from a single cop? In one of them, it's impossible. In the other one, it is possible. What do you think? So you don't have to answer me. I'll do a rhetorical question. I'm used to that. My students don't answer. I always, if I think about this, I imagine that this is like my kids watching television, and then they will shout out the answer. So I'm just going to believe that you do that. You're going to shout to me that it is the right-hand tree in which the robber can hide, and then you will be correct. If you look carefully, you'll see the only difference between these two trees is that the second tree has an extra leaf. And you might think that that is kind of intuitive. If you think about a real life situation where the robber should hide from a cop in a tree, then he will do better if there's more leaves, because then it would be more bushy and maybe you can hide behind the leaves. Like in this case, an extra leaf. This is not, however, not the reason why the robber can hide from a cop in a tree, but rather because of this substructure that's highlighted in red. And it was shown that this substructure, T33, is always a hideout from one cop in a tree. So it means whenever this is present, then one cop will not be enough. And I want to show you why this is true. What we do is we show that whenever we look at the area where the robber can be in the next step, let's call that the extended robber set. If the extended robber set contains one of these sets, either the red part or the green part, then we know that the robber can always go back to either the green one or the red one. If we can show that, then we're done. And the reason for that is because when we start, the robber can be anywhere in the graph, which means it can be anywhere in this special subtree, which contains the green and the red one. Let's look at the red case and show that we can always get back to one of these. So if we probe the vertex E in this graph, then B will be a distance 1, A and F will be a distance 2, but C and D will have the same distance away from the gray vertex. And therefore, the extended robber set in the next round would be this area, and we will be back at the green option. Similarly, if we probe the vertex B, the same thing will happen. We get back at the green one. So we don't have to check for probing at F or G or H or I or J, because that is similar at probing at one of these vertices. Similarly, we don't have to check C and D, because that is the same as probing at B. So if we probe at A for the last one, then the robber has the same distance at B, C, and D, which means we are just back at this whole graph in the next term, which contains both the red and the green options. We can do this, have the same argument, and say if we start at the green graph, we can always get back to one of the two as well. And this shows that the robber will always be able to hide in a tree. In fact, Seeger showed that this is the only substructure that we need to search for in order to know whether the localization number is 1 or not. And she showed that when this tree is not present, the localization number is 1, and if it is present, the localization number is 2. So from here, so if you think about how do you build up from a tree, so we've sorted out trees, there's no cycles. So now we would like some cycles. So we're just going to take it a little bit further. There's been some work done on planar graphs, and they've managed to show that for outerplanar graphs, we can also bound the localization number with 2. Now, our outerplanar graph is just a graph where all the vertices lie on the exterior region. So the interior regions will be these in black, or the black dots in them, and the exterior region will be anywhere else around that graph, and every single vertex lies on the boundary of the exterior region. Then it's called the outerplanar graph. This is a special outerplanar graph. It is a cactus graph, not quite a tree. It looks like one. So why are we interested in outerplanar graphs? Well, if we want to move from a tree to something with cycles, well, firstly, I don't want to go all out to an outerplanar graph and have many cycles. I'm just going to start smaller with one cycle. But if I have only one cycle, a unicyclic graph, then it would be an outerplanar graph. I'll draw the cycle and then just all the branches outwards from the cycle, and everything would be on the exterior region. And we want to investigate, if we have unicyclic graphs, will this special tree, T33, still be a hideout in a unicyclic graph? Unfortunately, it's not. So this was also shown by Seeger. If we have a cycle that runs between two sister vertices, so that's two vertices with the same parent. If we have a cycle that's large enough, must be at least of size 7, of cardinality 7, then the robber can't hide in T33. We have enough extra information to catch the robber with a single cop. So what do we do from here? Then we have to figure out, is this the only case of T33 where this happens? Does there exist other hideouts in unicyclic graphs? Because in the end, because the localization number can only be 1 or 2, it would be great if we can also characterize unicyclic graphs. That's our current work. So we've managed to show that the localization number, that for a hideout for the robber in a graph can be one of the following 3 things. The graph T33, such that no 2 leaves with the same parent lie on a cycle. So it's all subgraphs with T33, except for those that looks like the one in the previous slide. But then on the exception, we have an exception, and that's the graph R1. I like to call it the Rudolph graph. Looks like a reindeer. And if you look carefully, you'll see that over here we have T33. And this graph has a cycle between 2 sister leaves. So according to the first sentence, the robber might be able to hide there. But if it happens that we have exactly such a copy, just one away from it, here's another one, then the robber can hide again. And the reason for this is because the leaf is that parent of the other copy of T33. It's a little bit of an exception. Then the third graph where the robber can hide would be in the corona graph, very fitting for our time. So that is a cycle with just pennant vertices to each of the vertices of the cycle, spiky corona. And what happens here is that the robber can just run around in a circle. The cop will not be able to find a winning strategy in that case. So we are busy looking at a strategy for finding the robber with a single cop when these graphs are not present. That's one of the things that we want to work towards. I'm going to end off with some open questions of where we would like to take this work. Firstly, I have shown many hideouts throughout this presentation where a cop can hide from a certain number of cops. In fact, we've shown hideouts when they can hide from one single cop. But it would be really great if we can find substructures in graphs where a robber can hide from k cops, so not just from a single one, so that we can build up certain lower bounds to say that if this restrictions of subgraphs, if this subgraph is present, then we know the localization number must be greater or equal to k. Then continuing with this last idea of outerplanar graphs, since we know that outerplanar graphs can only have localization number 2 or 1, the main goal would be to characterize outerplanar graphs. But before we get there, we're just going to take baby steps and try to characterize unicyclic graphs. Then after that, we first have to look at the kind of hideouts that happens in outerplanar graphs. We saw that if we take the hideout of a tree and we just add one cycle, then the hideout already changed and there's a lot more that gets added. So what happens if we have more cycles? Will these hideouts change? Most likely. And then what do they look like? And then if we have these, how can we characterize outerplanar graphs? Can we find a strategy that will always work for one CoP if these aren't present? The final thing that I want to chat about is edge removal. So this is about what happens to the parameter if we change the graph. So if we think about a 6 cycle, I'm going to leave you to convince yourself that we can't find a robber on a 6 cycle with a single CoP. So we know that the localization number must be equal to 2. If we take away one single edge from a cycle, we get a path of length 6. And a path of length 6 certainly does not contain that copy of the special tree T33. So the localization number is 1. That means if I remove an edge, the localization number will decrease. But if we look at that double house graph that we had when we showed that the localization number is 2, it is not necessarily to take away V and both the edges to increase the localization number. Even if we just take away one of these edges, we increase the localization number to 3. So we've seen that there exist cases where the localization number increase. There exist cases where the localization number decrease. There also exist cases where it doesn't change at all. So then we have to ask ourselves, when or what does these edges look like? Can I find a characterization for edges which will always decrease the localization number or increase them, so forth? We don't have to stay with edge removal. We can do edge addition and see what happens to the graph parameter if we add edges. Vertex removal, see what happens then. It will all be really interesting to see what comes out of this. Thank you so much for listening to me. That will be the end of it.
Wonderful. Thank you so much, Riana. I'm going to leave my video off and I'd like to welcome back our chairperson, Betsy, to chair the question and answer session. So as I mentioned before, please just post your questions in the chat or just unmute your microphone or raise your hand. And Betsy, over to you. Thank you.
Thank you very much, Diane. We enjoyed your lecture, Riana.
Oh, thanks, Betsy.
Questions. Who has questions for Riana? Augustine, what is your question?
Hi, good morning. Yes, I'm not a graph theorist, but I was attracted by the charming title of the talk. And I noticed that she has said quite a lot of things, many of them technical. I am aware that graph theories have this network of roads and things, and there's the studies that have been done in graph theory have been successfully applied in Germany in their road networks. I just want to know whether this theory here has found favor with the police in terms of trying to catch real-time thieves out there, because that is the one that really concerns the layman. So how are you getting on with the police and the law enforcement people with the theory? Thank you.
Thank you, Augustine. I see Nick has exactly the same question. So the short answer is no. No, this is just a fun way of understanding the problem. I have read in some of the first papers that they really try to motivate it by saying that it is applicable, but I highly doubt it. I mean, there would be easier ways to find the robber than trying to play this game. So this is purely theoretical exercise.
Any more questions for Riana?
I can't raise my hand, but I'm going to bounce off something that Augustine said.
Yes, please.
So I enjoy mentioning frequently that I'm not a mathematician, but you know, having said that, my role at the center does involve science communication in terms of real world applications.
Mhm.
And it's kind of maybe not a question that's easy to answer, but if I can impose it on you, Riana, like what, you know, in terms of moving from graph theory into application or practical application, if you like, can you give me any idea of, because I've got some idea obviously of where graph theory is applicable, but just in terms of this theory.
Okay, so I really don't know where this theory specifically is used, but I would think that if you think of graph searching algorithms, then these ideas can maybe be applied in searching for something on a network. And now this might not be cops and robbers searching for it, but maybe something less human-like on a computer network, for example, but employing some form of algorithm doing it. But I really can't think of something specific.
No, that's perfect. Like I think it's exactly what I thought. Sorry, Betsy, back to you. I know there's another question in the chat.
Is there another question in the chat? Now let me just...
So I can read it, it's fine, Betsy. Nick
Okay.
said, presumably you know the game battleships. Yes, I do. Could something like that be posed in a similar way? So then you will receive information. Oh, that would be lovely to receive information regarding your probes from the other player. Say that ship such is so far with the distance away from your probe. Is that what you mean, Nick? Or the idea you have? I can think that I think the game would end quite sooner maybe than in general. Because it's very structured. So this is just the Cartesian product of two paths. I think you would quite easily be able to do this. In fact, let me quickly think, because my student did, a master student of last year, did work on the localization of products of paths, and I actually think it is two. So now I wonder, with what do you do in battleships? You just probe one. Yes, you do. So, but in battleships, the ship doesn't, so if we let the ship move, this would be interesting. Yeah, but you could do something like that. It would be, because there would be extra information regarding the dimension of the ship. So I would suggest that you start with just playing with one ship and it has a specific dimension, and then you get the distance away, the closest distance to that set, for example. I think that sounds interesting. You can do that, yeah. I don't know if what I said helped Nick or hurt.
Yeah, no, if I can add to the conversation, what Augustine and Diane said, since it's still only about, say, only one cop, and I think it will be more applicable later, perhaps, if you work with a lot of cops, and hopefully not a lot of robbers too. But yeah, just thinking about that, perhaps.
So yes, so I'm just trying to think whether there's a game where there's more than, I'm pretty sure there's a lot of variations on these types of cops and robbers games. And I do think there are variations where there's more more robbers as well. But certainly this one extends into having more cops as well. So we're looking for that minimum number. So in some cases, we do need more than one or two cops in order to find the robber.
Okay.